Okay, a student, it's always a student, isn't it? Is given an unknown electrical component in a sealed box. He carries out an experiment to identify it. He sets up the circuit below. Have a look. So, complete the labeling on the circuit diagram. 4 marks for this. So, this is obviously your cell or your battery. They've given you the fuse. The wire goes through it. An ammeter. Oh my god, these are such easy marks. Your VR, variable resistor, and your voltmeter there. Complete the labeling on the circuit. Oh yeah, so we've done that. Sorry, a bit of a moment there I had. To prevent the unknown component being damaged, the current through it must not be greater than 150 milliamps. Circle the appropriate fuse that should be used in this circuit. So if it's not going to exceed, if it can't exceed that, it's pointless using a 200. It's pointless using a 500. Now, do we use a 10 or do we use a 100? Well, 10 is not going to give us any readings at all. So 100 is the best one to use for that. State the current in amps when the voltage is 1. Well, let's have a look. When the voltage is 1, it's got 50 milliamps. Now, we need to kind of convert that. So if you can think of a millimeter and then a meter, so there's 1,000 millimeters in a meter. And we can see this. So there's your multiplier. Look, a milli for anything like a millimeter or a millisecond. There's going to be 3 zeros. So it's going to be 0.00. So that's all that minus 3 means. There's 3 zeros before the number. I know that it's kind of hard to explain there, but just so the best thing to remember here is and I hope this comes out, is BSM SBD. Be smart, mate. Stop being dumb. Okay. If it's going from big to small, you're going to multiply. If it's going from small to big, like it is here, because we need to get it to amps, from small to big, so from a milliamp, from a millimeter to a meter, or from milliamp to an amp, I need to divide by 1,000. So that's probably the best way. I think these things confuse kids a lot of the time. But yeah, if it's from small to big, divide by 1,000. And that's how I've got that answer there. Because 50 milliamps is the same as 0.05. And if you can see, 50, it's moved 1, 2, 3, and that's why you got that 0.5. We don't bother putting a 0 on the end there. I need more pages. Yeah, I should do this in 20 odd. Use the equation resistance, voltage, current, so VIR, triangle, to calculate the resistance of the unknown component at 1. So I'm just using now the proper amps. It's got to be an amp, so 0.05. Voltage is going to equal 1, because it says there. And it's going to give me 20 ohms. And then I think use your graph to find the current. So plot the data. So it have plotted the data. Now we can already kind of tell what it's going to be, because it did move and then it shot up at an increasing rate. Use your graph to find the current when the voltage is 0.7. So that's my pink line there, 0.7. I brought it back and I've said 11 milliamps, because always check what it is. Oh, it's there anyway, it's given to you. And then describe relationship between the current and the voltage in the range 0.4 volts to 1 volt. Well, I've said as voltage increases, current increases at an increasing rate, because it shoots up. Again, I know that because for the amount of voltage I put in, there's not much current, and then for the amount of voltage I put in here, lots of current up top. And then identify the unknown component. Well, it is a diode, and we know that because it takes a while to kick in and then it shoots up. And that's the only graph that looks like that. And you can actually turn that into a D by adding a little circle, and that's your diode. The following circuits, this one was a tricky one. This caught me out. Okay, set up the investigate light dependent resistor. So a light dependent resistor is just a resistor that changes as light intensity changes as well. So here we got state two variables other than using the same component that should be controlled. Yeah, tricky one there. So you've really got to think about what's happening. You've got your bulb and you've got your dependent resistor here, and then they've just put an ohm meter in, which you would never have come across in this question, but it's kind of telling you an ohm meter measures the resistance really. But we don't have to learn about that. They've just put it in there to kind of throw you. So you need, because they're measuring the resistance from this bulb, what you need is from here to here to be the same distance. Okay, so that is one control variable that you need. So same length of wire. Same distance between the lamp and LDR. You also need the same background lighting. So if you were in, if you were doing this in a classroom and it was a really bright day, you're gonna need to keep the light conditions the same because anything can alter that. So a darkened room would be best. And then it's got the same length of wire, because if you increase the length of wire, you do change the resistance. So there needs to be the same length of wire as well. But I would say top two, even though I put that one there because the mark scheme said it, same distance and same background lighting would be the two that I would have got. Explain how the design of the experiment could be improved. Well, enclose the lamp and LDR in a container, so you make it darker so there's no ambient light from the room. So these two you're putting in a room on their own, or in a box, sorry, not a room, so that you're getting rid of the ambient light. The results are shown in the table below of what they've got, so be careful now because you've got kiloohms and you've got watts. So you've got power against resistance. When you plot your data, that's what it's going to look like. The scales are fine. You've had to come up with your own scale there. So that's my scale, and because the highest number was, oh my god, what did I just do with that one? Because the highest number was 19.5, I needed to go to 20, and that was my best scale to go to 20. The bottom scale was given to me, and then you can see my curve ain't the best there, but it'll do. And then the last page, use a graph to find resistance to the LDR when the lamp is a power of 2.6. 10 watts. I'm giving you the answer there. So 10 watts, see I've drawn my line because they've gone up in fours. We always advise not to go up in fours, because where's one? One is going to be like a half a square there, isn't it? If that's 2, 1 is there, half. Anyway, I brought that back to be 2.6, wasn't it? 2.6. It's going to be 2.6 kiloohms, but what's it going to be in ohms? Well, I'm going from big to small now, so I need to multiply it by 1,000, and that's how I've got 2600 ohms. Okay, I know I've put a K in there, but that should be the answer, 2600 ohms. It is suggested that when the lamp doubles, the LDR resistance halves. Explain using values from the table if this is true. So for 3 marks, I've said sometimes it's true, because at 12 volts, the resistance is 2.2 kiloohms, and then at 24 volts is 1.1. So yeah, that would suggest that it does. All this information, by the way, I've got from the graph. Okay, so at 12 volts, okay, I've gone across, and then at 24 I've gone across as well. But the same with 2 volts and 4 volts, resistance halves from 19.5. So all this data from the graph, but it's not true if I take 4 volts and then 8 volts, which is obviously double, because it's asking me if the power doubles. Why have I said volts there then? I think I just picked up a mistake. Yeah, I'm so used to voltage being on the bottom. So there's my first mistake. I should be saying watts there. I'm going to have to change that now. Yeah, even by ear. So at 12 watts, it's that. And at 24 watts, it's that. 4 watts and 8 watts. it does not half. Okay, it does not half here. So sometimes it's true, sometimes it's false. And that's that paper. Chunky little paper it is.